Hello, my name is Zorka, and my thesis focuses on linear encoding and decoding of brain activity in response to music. When you listen to music, your brain doesn't just receive sound, it actively tracks it. Neurons fire in patterns that follow rhythm, the notes, and the loudness of what you're listening to. And those patterns are strong enough that we can measure them from electrodes placed in the scalp using a technique called EEG. The problem that I focused on is that most existing research on how brain processes sound is done on speech and not on music. And I will be focusing on music. There are a few studies which looked at music, and almost all of them went in one direction, only encoding, which is predicting brain activity from the music. But what I will be doing is focusing on both encoding and decoding, where decoding is reconstructing the sound from the brain activity. Also, not many researchers have been focused on different acoustic features and then their combinations and how they influence the encoding. I will also be separating EEG into several frequency bands to see where we can track the brain activity the best. Specifically, this thesis will be asking 5 different questions. Can the melody someone is listening to be reconstructed from their neural data? Can neural data be predicted from the music someone is listening to? Does increasing the number of acoustic features improve prediction performance? How does performance vary across frequency bands of the brain activity signal? And does the musical expertise lead to measurable differences in neural responses to music? In order to answer these 5 questions, I have used the publicly available EEG dataset. The dataset had 20 participants EEG while they were listening to music. 10 of them were professional pianists with over 10 years of experience, while the other 10 were non-musicians. The EEG had 64 electrodes placed on each participant's head, and they were listening to 10 different bass pieces. 10 different pieces were played 3 different times, yielding 30 trials per participant. In order to analyze music, which is a complex sound, I first separated music into several acoustic features. The envelope, how loud the music is over time. The onsets, when each new note starts. The pitch, how high or how low each note is. The spectral centroid, the brightness of the sound. The MEL spectrogram, how energy is distributed across frequencies, and the MFCC3, a compact descriptor of spectral shape. For extracting these 6 features, I built 2 different pipelines. For the first pipeline, I analyzed first 5 features: onsets, envelope, pitch, spectral centroid, and a MEL spectrogram. In the next process pipeline, I analyzed the first 4 features with MFCC3. So the MEL was only in the Bro pipeline, and the MFCC3 was only in the process pipeline, and the first 4 features were in both. The comparison hasn't been done before on this kind of data. It directly addresses one kind of gaps that I identified in the literature, which is that pipeline was not used as an experimental variable. In the Bro pipeline, features were extracted using Librosa and EEL-Brain. For the process pipeline, each feature was also standardized, and when it comes to onsets, it was also smoothed with a low-pass Butterworth filter, which kept only the slow changes and removed the fast ones, so the small spikes are not visible anymore. And for the pitch, it was computed as the absolute first derivative of the fundamental frequency, and in the Bro pipeline, it was only computed as a fundamental frequency. When it comes to envelope and centroid, they were only standardized and nothing else was changed. On the brain side, the EEG in the dataset was cleaned and also re-referenced to the average of 2 mastoids that were placed as 2 channels here. On the bony areas behind the ears. What I have done with the EEG, I have separated it into 5 different frequency bands: delta, theta, alpha, beta, and also a wide band that covers all of them. Also, I have downsampled the EEG from 512 Hz to 100 Hz in order to match it with the stimulus that I've also downsampled to 100 Hz. I've separated EEG into frequency bands because in other literature, different frequency bands have been linked to different aspects of how brain processes sound. For example, theta tracks the rate of individual notes, while beta tracks slower rhythm in the music. After pre-processing the EEG and extracting features from music, I used a model called temporal response function, or TRF for short. This is a linear model that works with convolution, and it learns the relationship between a stimulus and brain response. For encoding models, for the input, I've used either 1 feature, 2 features, 3, 4, or 5 features. In total, there were 31 combinations of the features in both pipelines. For the decoding model, I have only used the EEG. So the encoding model goes from stimulus to EEG, and the decoding model goes from EEG to stimulus. I fit these models using a boosting function in Python. This function keeps only the most informative weights and discards the rest, making the results easier to interpret than other approaches. So TRF was fit for each of the 20 subjects, for each of the 5 bands, for 2 pipelines, and for the 31 combinations of encoding model and 5 combinations of decoding model for each features. This totaled 7,200 TRF models that I've used. These results were aggregated in one file in order to be used for the statistical analysis of results that I will be presenting now. We will be started from the decoding. The Pearson's correlation coefficient between the true and the predicted acoustic feature was the strongest in envelope and onsets, both in the row and in the process pipelines. When we look at the onsets, we can clearly see that processing the onsets in a different way than just doing the row onsets gave much better results. When we look at different bands across all acoustic features and both pipelines, we can see that the theta band consistently gave the best results. When it comes to envelope and centroid, we can see that there is not a difference between the row and the process pipeline, meaning that the standardizing of these features alone did not increase the correlation coefficients. Also, when we look at the differences between musicians and non-musicians, significant differences using the t-tests were found in several frequency bands, usually including theta, and most of the frequency bands in envelope and onsets gave significant differences between the groups. Here we can see best, median, and worst example of the each feature reconstruction. We can see that envelope and onsets, as I mentioned, are the best, and the reconstructed feature follows the true feature the best. This next decoding result was published on an AI and ML Audio Engineering Society conference last September and was also presented last November at a UCL Neuro AI conference. This results show that there is not only a difference between musicians and non-musicians in terms of how high correlation coefficient was. Musicians had stronger filter amplitudes than the non-musicians. And also, they had stronger voltage field, particularly over the right lateralized channels, which can be seen here with the stronger colors, while in the non-musicians, we can see that the results are more symmetrical. This aligns with prior findings on hemispheric lateralizations for musicians. When it comes to encoding results, we also see a similar pattern as in the decoding results. We can see that the theta band gave the best correlations, the musicians usually outperformed the non-musicians, and that onsets and envelope give the best correlation coefficients. Now, when we look at the effect of adding different features in both pipelines, we can see that in the process pipeline, when we add more features, we get better correlation coefficients. But when it comes to the row pipeline, we get worse results. Then I checked what is the reasons for getting the worst results. When we exclude MEL spectrogram from the combinations of the features, we can see that row pipeline behaves similar to the process pipeline. This means that the results were worse when the MEL was included. In order to see which feature contributed the most to the encoding models, I've used a multiple linear regression that was fitted per band and per pipeline. The results I got that the envelope and onsets contributed the most. When it comes to the process pipeline, pitch also contributed, while in the row pipeline it didn't. MFCC was non-significant, so it did not contribute meaningfully to the pipeline, to the process pipeline. And when it comes to MEL, it contributed negatively to the row pipeline, which also confirms our results from before. When it comes to centroid, in the row pipeline, it gave small significant results, while in the process pipeline, it not gave significant results. Now, with all of these results, I will be circling back to the research questions from the beginning. Can the melody someone is listening to be reconstructed from their neural data? The answer is to some extent. Envelope and onsets give good correlation coefficients between the true and the predicted features, while other features gave lower results. The second question, can neural data be predicted from the music someone is listening to? For these pipelines, the correlation coefficients that we got for encoding were much lower than for decoding, so the answer to this question would be no. For the third question, does increasing the number of acoustic features improve prediction performance? Yes, as we saw when we exclude MEL from the row pipeline, we get better results when we add more features, and for the process pipeline, we get the same results. For the fourth question, how does performance vary across frequency bands of the brain signal? As we saw, the theta band was best overall, and other bands give considerably lower results. And final question, does the musical expertise lead to measurable differences in neural responses to music? Yes, as we saw, in many bands, there was a significant difference between the groups, so the musical expertise does have an influence in the neural responses to music.
What does this project contribute to the field? It is the first to systematically compare 6 acoustic features across 5 frequency bands and 2 feature extraction pipelines for music EEG. It does this for both encoding and decoding on the same dataset while also comparing musicians and non-musicians.
So why does any of this matter beyond curiosity? Music and EEG together give us a window into how brain processes sound. And the better we are at understanding that, the closer we are to building brain-computer interfaces, devices that can help people who can't speak, or restore hearing through neural implants. Thank you.